Hiya. So in this video, we're going to be looking at other changes of variables. So basically things that don't necessarily fit into um, our previous ways of looking at things. So I'm going to go over through two examples. One of them is very similar to the many to one kind of thing. Just to give like another example that's a little more different, like it kind of makes you think about things. And then the second one is a lot more complicated. So basically, these ideas are taking off from the arbitrary continuous distributions. So I mentioned that we're not really going to be doing too much with them, but I do want to kind of do a few examples anyway, just so you kind of see how these might be used in like real life kind of setting. So so we're just gonna kind of go through them. Don't worry about things being extra complicated. Remember, these kinds of things we're not going to be doing too much in like either a homework or a exam setting. So don't worry too much. This is just more for you to grasp kind of how to do things for future whatevers. So the first problem we're going to look at is cutting a cake, because as we all have learned, apparently Aram loves cakes. I don't know, like half the examples I feel like are cakes. Anyway, so we're cutting a cake. So here let's imagining where we have a unit cake. So in other words, we have a cake where the radius is 1. So let me draw my cake. And you randomly choose a point on the side to start on. So we're going to choose a point. We'll say this is our random point. And here I mean uniformly at random. So we randomly choose a point. So if we think about this, so we're gonna let x be our x coordinate. So here, if I draw, let me draw a plane. This is going to be our x coordinate of where we cut the cake. And so what's the probability density and the expected value of x? So the thing to kind of note here is that our choice of point is also, since it's uniformly distributed, we can actually represent this in a couple different ways. The book does this in a little different way. So if you want to see a more realistic way to approach this, you can. I'm going to do this slightly differently because I find this method significantly easier. And then the next example, we'll look at how to break this down a little more difficultly, or not difficultly, but like in a different way. That's the diff word I wanted. So basically the kind of way to look at this is, if I look at my angle here, this is kind of what's uniformly distributed, right? As I go over from here over, this is my uniform distribution. So I can think of theta as a random variable. Which is kind of telling me my angle. And this angle is actually just going to be equal to where I am on this point. So the uniform distribution on 0 to 2 pi, right? Because I can go all the way around. It doesn't matter, right? I can go all the way around. And if I look at x here, well, how is x related? So if you think of SOHCAHTOA, this is cosine here on the bottom. So what we have is cosine of x is equal to theta. And so we can use our many to one kind of function to basically go from here. So what we have is, if you think about cosine looks like this, right? So it goes down up until pi, and then it goes back up until 2 pi. So we have to break it up into two areas. One where it's decreasing, and one where it's increasing. First thing we have to do is range, right? So the range, you can kind of already see it from here, right? This is from 1 to -1. But alternatively, the way to kind of do this is, like we had said, you break up your many to one functions into little chunks, and you look at those. So 0 to pi, and then pi, I guess this should be a thing, and then pi to 2 pi, and then we convert these using cosine. So cosine of 0, cosine of pi, union cosine of pi cosine of 2 pi. The reason why I'm doing it this way, normally if we just do cosine, right, this is cosine of 0 is 1, and cosine of 2 pi is 1, right? So if I add all of these, I kind of have this. So if I were to just do cosine here directly, I would get interval from 1 to 1, which is technically not true, right? We have all these other values. So kind of breaking it up where I have my intervals from decreasing to increasing kind of makes more sense. So here cosine of pi is -1, and here it's much more clear to see that my interval should be -1, 1. So this is the interval that I'm going to be working on for x. Next, remember what we have to do is take the derivatives. So let's take the derivatives. So this is 1. 2 is derivative. So let's take derivatives of both sides. Cosine of x is equal to theta. So minus sine of x dx is equal to d theta. Now we want to convert, oh, not theta. Wait, this is wrong. Wait, cosine of theta is equal to x. Oh my god. Y'all let me do this wrong. Horrible, horrible. It's okay, it's my fault. Hopefully you all weren't confused beforehand. Sorry about that. This is backwards. Theta, and then x. There we go. But obviously we're trying to convert everything into x, right? So how do I convert sine of theta into x? And here we're just going to have to remember, well, we have something in cosine, so I want to convert this into cosine. And how are cosine and sine related? Well, you should kind of remember that cosine squared plus sine squared is equal to 1. So in other words, sine is equal to 1 minus cosine squared square root. So in other words, sine of theta is equal to 1 minus cosine theta squared, right? And this is where we have the kind of plus or minus, right? The two different ways of looking at this. So in other words, here what we have is plus or minus sine theta, or I guess I can convert sine theta with this, 1 minus cosine squared theta squared, or yeah, d theta equals dx. So what this gives me is d theta divided by dx. So I'll move the x over, and I'll move the 1 minus over. 1 over, so I'll do plus or minus up here. 1 minus cosine squared theta. And cosine theta is just x. So this is just square root of 1 over minus x squared. Done. Okay, well, now we have to solve our function, right? Remember how we have fx of x, in this case, is going to be equal to all the possible summations of f theta over then the derivatives, right? Now in this case, our f theta, since it's uniform, is just 1 over 2 pi. So we have 1 over 2 pi, 2 pi, and then we take the absolute value of the equality. So here we would do absolute value of 1 over square root of 1 minus x squared. And then we would have to add the other one, 2 pi over minus 1 over square root of 1 minus x squared. These two become positive, and we can add these together. So we have 1 over 2 pi. We have two of these, so 2 square root of 1 minus x squared. So we just get 1 over pi square root of 1 minus x squared. Easy. So this is where our probability density is coming from. But we also asked probability density and the expected value. So we're not going to, well, we will solve the expected value. I don't have enough room, but I'll do it here on the side. So if I look at the expected value here, well, my range is from -1 to 1, right? Expected value of x. I take my function, my probability density, which is 1 over pi 1 minus x squared, and I multiply this by x. Now the thing to kind of note here is that this is actually a symmetric function. So if you were to draw this out, you would get a symmetric function. And the symmetric function basically looks like this. This is what it looks like. And so since it's symmetric, like, since it's symmetric around the, like, it's an odd symmetry, right? Which means everything has its opposite. Like this part here is the same as this part here. Another way is to kind of look at noticing that this is symmetric as well. So what you end up getting is, since you have an odd function, what you have here is that this is just going to be equal to 0, right? If I look at this area and this area, they're going to be the same. So they cancel out. So the expected value is just equal to 0. So instead of having to figure out what the integral is, you can just do this, and you're nice and easy. You could technically do the integral as well if you really wanted, but you don't have to. You should just end up getting 0. All right, nice. Now we get to the more difficult part. So before you make the weird cut, your cousin looks at you and asks for your knife before you cut yourself. So here, let's kind of draw my circle again. And what you were planning on doing is cutting anywhere on the circle, right? It didn't matter where. And what you say is you can't just cut your cake from any side, right? It has to be from the top half. What this is basically saying is, so here's you. Here's your cousin. And what this is basically saying is you want to cut from just the top half, right? So when you normally cut, you're not going to cut from this direction, right? That's kind of weird. Like, you're not going to go in and out. No one does that. Everyone cuts from the outside in. So really, he basically says, no, you don't have that distribution. You have the wrong distribution. Really, you should be cutting from away from you towards you. So in other words, you want to look at when x is positive. He has the knife, so they will be cutting for you. So they'll be cutting in this direction, right? And these are all positive values. So in other words, what we're saying is we're going to let y be the absolute value of x. Right? We're looking at when we have x being positive. And we're going to solve the same thing, but from a positive standpoint. So let's kind of look at this. So if I take the absolute value, so first we have to do range, right? So if you think about this, again, absolute value looks like this. So it goes down, and then it goes up. So again, we have to split at this 0. So my range -1 to 1, I'm going to have to convert into -1, 0, union 0, 1. And then I take my absolute value from here. So here I do y is equal to absolute value of x. And so here I get -1, 0, union 0, 1. Nope, there we go. And so what we have here is 1 and 0. So we get 1, 0 as our interval. So nice and easy, not too bad. Another thing we can kind of notice is, well, every point from before is getting sent to one thing. So like, you can consider everything from before just going to one particular point. So every point on this side, let me try a different color. Every point on this side is associated to some point on this side, right? And this is basically done through this like opposite thing, right? So this point here is associated to this point when we do cuts. So in other words, we don't really have to calculate. So here we're again asking, I guess, let me see what we're asking. We're asking for the probability density function and the expected value. So since all these points are basically the same, what we're basically saying is, well, we're just doubling whatever our f is. We're basically mapping everything to something else. So in other words, what we have is our probability density function for this y is going to be equal to 2 times our probability density function of x. And this you can kind of see if you do this whole approach from above as well, right? Because what you'll end up getting is, because you'll end up on the bottom, dy dx. This is either -1 or it's 1, right? And then taking the absolute values, we'll get 1. We'll get 1 on top and 1 on the bottom. And so that's why you just add them up, 1 plus 1. So we get 2 times f of x, f sub x of x. And so we get 2 over pi, square root of 1 minus x squared. But notice how I have x squared here. Here we just plug in x and y, right? Since x and y are basically the same, since we're squaring it, right? X squared is equal to x squared is equal to y squared. So they're identical. So we have this for f sub y of y. So what's left is calculating the expected value. So what is the expected value of y? Now this one's a little more difficult because we have this 2 in front. Not only that, but we no longer have our symmetry, right? We're going from 0 to 1. So we have 2y pi square root of 1 minus y squared dy. At this point, you should kind of recognize that, oh, I should probably use substitution. So here, let me make it z, and I'll say it's 1 minus y squared. And here dz is equal to minus 2y dy. So in other words, dy is equal to dz over minus 2y. So plugging this in, remember we have to keep track of our bounds so we don't screw them up. And then we have 2y over pi times the square root of z. dy becomes dz over minus 2y. So in this case, the 2y's cancel. So we have less things to worry about. Here I can also translate my bounds, right? So y0 implies 1 minus 1 squared, which is just 0. And this is 1 minus 0 squared, which is just 1. So what we end up having is 0 to 1 of dz minus pi square root of z. So here, oops, wrong way. 0 on top, 1 on the bottom. So what we have is this minus I can use to flip the sign, right? So I can do 0, 1 dz pi square root of z. And here I can take my integral, 1 over pi. I add 1 to the exponent and divide by the exponent. So I get z to the 1/2 divided by 1/2. And this I want to do from 0 to 1. Plugging in 0 gives me 0, so I don't have to do anything. So really it's just this 1. So 1 times 1 to the 1/2 over pi times 1/2. This is just 1 on top. This is 1. And then so what we're ending up with is 2 over pi. And that's it. So that's one example. As you notice, it's a little long, and that's why I mentioned this is not something I'm going to do for an exam, right? This is way too long for an exam. Okay, so that's it for this example. In the next video, we'll see another example that's even more complicated in order to see how to do things in a little more complex way. And I think it's pretty cool. So I'll see you then. Bye.